I think everyone is about seated now. So, this is Luan. He is the founder of Flame, which I'm also a part of. We're actually a team of 5, 6 now.
6.
Yeah. So if you haven't tried out Flame, you should do that. But today will be both about Flame and about real 3D.
Yes.
We had a talk previously about fake 3D at FlutterCon, right? But now we're moving up in the world to
Yeah,
real 3D.
exactly.
Next talk next year will be 4D. After that, 5D, etc. So
Yeah, basically every year we're gonna add a dimension. Yeah.
Yeah, give it up for Luan.
Hello, everyone. Welcome. Thank you so much for having me in Stockholm. So yes, as Spyron said, last year we had the pseudo 3D talk. And you might be asking, are we talking about 3D again? Well, this one is very different, I promise. There's some similarities, but you can think of it as a continuation, because basically on the previous one, we talked about how we can leverage the tools that we had at the time, which are mostly 2D tools within Flame, to make games that maybe look and feel a little bit more 3D. But by the end of that talk, I was talking that there is this thing called the real 3D, right, that we quite didn't support yet. But that was last year, and now, well, things changed. So let's get started. So this is me, Luan. As I said, I work with the Blue Fire organization with a few other people. We make the packages you love, like Flame and all the ecosystem, audio players, all the bridge libraries that we use for making games. And as he also said, we had this talk last time about Flame, and basically the whole point of that previous talk is I said I was going to answer this question, because I get asked this a lot. People ask a lot, so does Flame support 3D? And I said back then, this is a very complicated question, and basically it took the whole talk to kind of explain this. So I'm going to have to do a summary this time, because I want to get further into some of the answers. But basically, why is this question complicated? Because you say, oh, it's a simple question, right? Does it support 3D, yes or no? Well, no, it's not that simple. Because what do you mean by Flame? What do you mean by support? What do you mean by 3D? And we explore all these topics on the other one, but mostly what do you mean by 3D? And basically, my point last time is that there is this whole spectrum of games, of how they look, or how they can feel like 3D. But by the end, I said, well, there's this real 3D, and I showed this FAQ. So I went to the FAQ of Flutter on their website, and I scrolled down, and well, Flame is built on Flutter, right? So if Flutter doesn't support it, Flame won't support it. And I looked it up on the Flutter FAQ, and it said, can I build a 3D OpenGL game? And it said no. I added it natively there, kind of, because you could do some hacks, but you wouldn't be able to natively support. So a few days ahead of this talk, I went back to the FAQ, and I looked it up again, and it's still there, exactly the same, didn't change. So yeah, nothing changed, that's all that we have. So no 3D. No, that's not true. Everything changed, because we got this article, Getting Started with Flutter GPU. So this Brandon, or Bidero, has been working on this for a long time, and basically he implemented support for accessing the real GPU within Flutter. That's using the new rendering system called Impeller, and it basically allows us to do a lot of different cool things, even within 2D. But one of the things that it unlocks is that it unlocks this new kind of 3D that we didn't see last time. But I think we're getting a little bit ahead of ourselves. Oh, another important thing, I added this note caveat that I'll talk more about some caveats later. This is very bare bones, but this right now only works on Mac, so that's why I got the Mac here. I tried to hide my shame a little bit. I put a sticker there, but yeah. So we're trying to get ahead of the curve and basically implement what we need in Flame to get this rolling. So when they support the other platforms that Flutter supports that we all love, we'll just kind of get that for free, which is the whole point of Flutter. But let's go back a little bit. So when we talk about 3D, what is 3D? So I make this slide just to get this out of the way. There are things I'm not going to mention at all that are out of scope completely for this talk. So the first thing is when I say 3D here, what I mean is 3 dimensions of space, and that's it. I'm not talking about time as a dimension. I'm not talking about, I'm a physicist, so when you talk dimensions. You might ask how many dimensions the universe has, and there might be 4 dimensions, or maybe some people say it's 11. No, let's think normally like the world as we know has 3 spatial dimensions, right? And not only the world we live in, but when we make games, we're simulating fake worlds. We're creating, imagining new worlds, right? But normally they're going to be 3D as well. Of course, you might have like a book like Discworld where the world is actually 2D, but in 99% of the normal games that we play, regardless of how it shows on the screen, in your imagination, that world is supposed to be 3D, right? So that's one part. And then right at the other end of the spectrum, you have this game being rendered on a screen, on a monitor, that is actually 2D, right? Well, it is a 3D object that exists in a world, but the surface of the screen where we have this grid of pixels is 2D, right? So somewhere in between, there is some disconnect. It was 3D at some point and then become 2D. So we're going to talk about this transformation, where exactly it happens, because that's where the magic is. I will also mention only this time that if you're not rendering your game in a typical screen, so maybe you have like a VR game, that could be real 3D, like actual 3D, or if you have those 3D goggles, you can watch the movies. I guess you could make a game as well. I've never seen one, but I don't see why not. Or maybe you have some hologram. Of course, you can render things in actual 3D, but for all intents and purposes, for 99% of the games, we're talking about games that are rendered in a 2D surface. So even when we say a 3D game, we're talking about a game that has that is being shown as 2D, but feels like 3D, basically. And it's supposed to be 3D in our minds. So this is kind of, so the whole question is like, we have this 3D thing being rendered in a 2D surface. So what is this transformation? So I divide in two types to begin with. This is the transformation that we're going to learn, this yellow arrow here. I divide in two types. So as I said, in both types, I think in our imagination, the world is 3D. But there are two very clear, distinct types of games in where in the code, the world is 2D, or in the code, the world is 3D, right? So what do I mean by that? If you have like some top-down game, you're saving, like you have the player character, and it has its position as an X and Y. That's 2D in the code. And then it's shown as 2D on the screen. Or you have your player character has a position X, Y, Z. It has a vector 3 as a position. That's what we're going to show they're going to be calling the real 3D. So last talk we'll focus more on number 1 here, but this time we're going to focus on number 2, and more specifically we're going to focus on this arrow here, which is the transformation between the 3D coordinates in your code to 2D coordinates on the screen. Okay, so let's do a quick recap from last time. We talked about 2D worlds. I think there are 2 key takeaways from 2D worlds that are going to be important this time. The first thing we learn about the 2D version is that even though we're going from 2D to 2D, there is still a transformation involved because we have a camera. Because normally in most games, you're not seeing the whole world at the same time. You're seeing a section of it. So you're already transforming from world to screen coordinates. It just happens to be 2D to 2D. But the way you do that, that's the second takeaway, is we use matrices. And these matrices are coordinate transformations that we're making to transform one thing into the other. And this talk, I'm not going to go deep into the matrices, because that was more the point of the previous talk. And for this one, we're kind of going to abstract that away a little bit. But it's important to know that all these transformations are basically a 4x4 matrix. And here's an example of one for 2D, but we're going to see that the 3D is not that much different. It's actually, we're doing very similar things. And then in the last talk, we also saw some 2.5D techniques, or ways to make the 2D worlds kind of look and feel more 3D. Again, we're not going to talk about this, but if you want to know more about any of one of these topics, you can check out the other talk. We're going to talk about the real 3D, right? So we are going to keep pressing this, like, what is real here? What do we mean exactly? Well, we're talking about 3D rendering, right? But more specifically, we're talking about a 3D in your code, right? So as I said, you could think of a simple game where you have this like player class, right, or enemy or character or whatever you have on your screen, and it has a vector too, has an X and Y. That's what I'm calling a 2D world. So, and in this one, you also have a transformation. You have like a camera, but it's a much simpler transformation. So this is not what we're talking about. We're talking about 3D worlds where you have 3D objects. So you have vector 3 to represent their positions. but still you need to render that into the flat 2D screen. So what's the transformation here? So let's refine our understanding here, and we're saying we're 3D world rendering. But that's not only that, because last time, we need to find this transformation function. That's going to be a piece of code that's going to transform coordinates from the 3D space into the 2D space. And I'm already giving a spoiler here that it has to do with triangles. But in essence, in abstract, we're thinking like anything, any coordinates could be transformed from one to the other, right? And it has, everything is unlocked by this question. This question gives us a hint of how we're going to do that, because it says, can I build 3D worlds, parentheses, OpenGL. So we're going to see a little bit more about what is OpenGL and how it fits into this. So basically, there are two ways we can do this transformation. So we have our 3D code, and we want to transform that into 2D, right? We can basically do that into the CPU or in the GPU. And last time, I showed how to do it in the CPU because we didn't have this GPU access available. So you can definitely do that in the CPU. In fact, that's how games used to be made, before these fancy GPUs existed. And I showed this video that's from last time. It's 3D rendering in Flame. So this is similar to what we're going to accomplish, but this is all done in the CPU. Now, this is not very optimal. Of course, for this very, very simple example, and even something a little bit more complicated, it should be totally fine, but it won't scale forever. It will not, well, nothing scales forever, I guess. But it'll not be as fast as using the GPU. And the reason is because they work fundamentally different. So the CPU processes does one operation after the other. It's very sequential. Some asterisks there, but it's basically sequential. And this operation we can think of, basically it's multiplications that we're doing. We're doing lots of multiplications. And the CPU, if we're doing only one, it's actually faster than the GPU, but it only does one at a time. When you have a problem where you're actually making multiple multiplications involving the same numbers multiple times, and you happen to be able to put that into the GPU way where you do them in parallel, you can see that it can be orders of magnitude faster because you can do thousands of a time. Even if your CPU has multiple cores, it won't be a match for a GPU that can parallelize in a much larger fashion. So we're very interested in going the GPU route. And so how do we access the GPU? The code you write, you have your dark codes, you're writing a Flame game or anything else you're writing basically, is mostly run on the CPU. So in order to unlock the power of the GPU, that's where OpenGL comes in. So OpenGL is one of many protocols or interfaces or ways or programming tools that you can use to access the power of the GPU and do things in parallel the way we want to handle these graphics with. And there are others. So OpenGL is the good one because it's free and open source. So that's what we're going to find in Linux and Android and that kind of stuff. But if you're on macOS, you have Metal. That's, again, same deal, different API to do the same thing. And if you are on Microsoft, you've probably heard of DirectX. That's, again, the same thing. It's using GPU 3D, not only 3D, could also be 2D, but GPU rendering in general. And we're not going to have to deal with these specifically because, as we're going to see, we're going to have a wrapper on top, which is the Flutter GPU package. And the way these things are normally used is to make 3D games. In fact, most, big, I would say pretty much all 3D games these days, big or small, are made using these libraries and using the GPU as a way to render 3D graphics. So you're definitely familiar with this from just playing other games. But the GPU, I wanted to mention, can also be used for other things. In fact, it was originally envisioned for graphics because they realized that graphics is basically just multiplying a lot of matrices. And I'll say that a lot of times because basically that's all that is, multiplying a lot of matrices. And they designed this different type of processor that's better to do that than the CPU. But then later they realized that there are other problems that they want to solve that also involve multiplying a lot of matrices but are not rendering graphics. So they created other languages, other protocols to access. We're not going to talk about that. A very famous one is CUDA from NVIDIA. So you might have heard of that in the context. There's recently been this new thing that everyone has been using GPUs to do. Oh no, sorry, the actual new thing that everyone has been using GPUs to do instead of graphics. They use these languages, but we don't care about that. We're actually using GPU for its original purpose, which is graphics. So we're amending to our definition here. We not only want the 3D world rendering, which we did last time with CPU, we want a GPU accelerated 3D world rendering. And not only that, I'm also gonna add that we want our first class. So we wanna use this new Flutter GPU package that was provided by us, by the gods of Flutter, and gives us direct access to this instead of some, plugging like indirect access approach they could potentially try to do before. So this is our complete problem statement. So the real 3D that we're seeking is using Flutter GPU, first class Flutter package, kind of built into Flutter, basically, built into Impeller, to render 3D worlds using GPU acceleration. So the question is, can we do it? And yes, we can now do it, kind of. A little bit. But so this is very, very, very bare bones. As you saw, that article was very recent. This has been working on for a while, and as the Flutter team has been working on Flutter GPU, we have been working on Flame 3D in the background at the same time, but it's still extremely bare bones. But I think that's kind of how Flame is. It's like you could use any other game engine, right? Like there are much more mature and established engines out there for you to pick. And I feel like a lot of the Flame is like this exploration and kind of being the pioneer and figuring out how to do things yourself. It's a lot of pick and choose things that Flame will help, and then combining with some things and doing your own thing. And also ties to this like code first approach of Flame, where you're basically, everything is code, and you might need to extend some Flame class to add something that's missing, or you might send us a PR. So if you're willing to partake in this very initial stages, yes, we can get something done. And well, as I said, it's gonna be bare bones. So I'm already gonna start telling you that just to set it up is gonna be a little bit complicated. So we have the Flame 3D package that's published, but you probably, if you're gonna do this, I recommend you clone all the repos and do a pub/spec override, so you have always the latest versions of everything. And in fact, you're gonna have to use the Flame 3D branch in the Flame repo because this is not merged. So the Flutter code is still in main, and Flame depends on stable. So this is not actually merged into Flame yet. So you're gonna have to do some branching, and in fact, there's some other branches you might need. So for example, I've been working on animations with joints. So if you want that, you're gonna have to grab this branch. And I also published this Flame 3D Extras package that has a lot of code that hasn't been ported into Flame yet, but they work together really well. They're all connected. So you're gonna have to do some scrapping, putting together some packages to get this working. But basically, as an overview, what we're thinking to do is here you have your code. This is your game, right? Your code, and you're gonna be calling just Flame. So the idea is you're not gonna have to interact with Flutter GPU directly because Flutter GPU is very, very low level, and we wanted to make it easier for you to provide a more high level API that you're more familiar with from 3D in other game engines. You're also gonna interact with Flutter directly, of course, because you still might want to render, the old 2D stuff, or you might want to have interface on top of your game. But basically, your code will interface only with Flame and Flutter. And Flame, I use Flutter as well to do the old CPU 2D rendering. But it will use Flutter GPU. So Flutter GPU, as I said, is basically a wrapper on top of an arbitrary middle layer, depending on the platform, how you access the GPU. This is a little bit of a stretch because, as I said, right now it's actually only Metal, but I'm going to be saying OpenGL because that's what everyone uses as a standing. But ideally, in the future, it would be Flutter GPU is a single interface to access any of these, and then that connects to the low-level library, which connects to the bare metal, which is basically the bits, and that renders on the screen. So this is kind of the plan. So what I'm going to show you is how Flame 3D works and how you can use it to render things today. So let's see what we have. Before that, I'll make a preamble that a lot of this code was made not only by me, but especially by Johan, or Wolfen Ring, as is known. So I'd like to give a huge applause for him, please, because this wouldn't be possible without his help. And let's start with triangles. As I said before, I gave a spoiler. I said everything's triangles. I also say everything's matrix multiplication. That's also true. Actually, they're both the same. And basically, this is what everything is. So let's start with triangles. So basically, we're talking about a transformation between 3D and 2D, right? Because in the end, we want to render things on the screen, which is 2D. But in the beginning, we have 3D points. Well, not exactly. We're going to arrange those points as a triangle, because triangle is the simplest surface that you can have in 3D. And with triangles, you can build any other polygon, and you can approximate any shape as well, even if it's round. We're just going to be using triangles because as you might suspect, computers don't do well with round things, so we just approximate everything into triangles. And then basically what we want is this arrow here, which is how do we transform a triangle in 3D space into a triangle in 2D space. Now, I talked a lot about this on the previous talk because we did this basically by hand in the CPU. And we learned that it was all about matrices. And everything we're doing is always multiplying matrices. And this is the second time and final time I'm showing matrices to you, because this time the Flame 3D package is going to do a lot of this for you. So hopefully, I don't think you're going to have to know what goes into any matrix, so the numbers inside. You might need to know that they exist, and you might need to know how to create them for certain scenarios. So basically what they are, a matrix is an affine transformation. It's transforming something into a different place. And that includes 3 operations: translation, scale, and rotation, right? So if you have something here and you want to move it, you apply translation. That translation by itself can be represented by a vector tree, right? You're displacing this by a certain amount. But you can put that into a matrix, and the matrix is kind of the standard form, because if you do a scale, you could also represent that for a vector, but that's different than a translation, right? So you put that somewhere else in the matrix. And if you have a rotation, in 3D, rotation is a little bit more complicated because you can rotate around any one of the 3 axes, right? So basically, you have 3 angles. So you could use a vector that has some problems. So instead, you use a quaternion, which is a more advanced way of describing a 3D rotation. And if you put all these 3 together, you get a single matrix. And the key thing to know about matrix is if you have 2 matrices representing 2 transformations and you want to apply both to the same object, you just multiply both matrices. And you get a new 4x4 matrix that represents the combined transformation. So that makes it very, very easy to keep adding transformations because you keep getting more and more matrices. And as you eventually come to realize, everything you're doing is multiply matrices all the way to the end. But these matrices will hopefully be created for you, so I'm not going to focus on the details on them. The other thing you need to know about 3D is that, as with 2D, you have the camera. That's very important because we need to know from where we're rendering things. But the camera in 3D is much more advanced. Not only it has the position, so that's where it is in space, and then it has a direction, that's where it's pointing at, so you can think of it like this laser beam, right? So it's looking at that. And also, this is a little bit confusing, but it has an up. That's because you can think, even though it has a fixed position and direction, you could rotate the camera, right? And if you rotate it like this, the picture is going to be upside down from how it was before. So you also need to specify the up, which is basically the rotation of the camera. The other terms that you might see as you start to play around with Flame 3D, depending on how deep you go into the cameras, are these. So basically, the camera is representing a perspective projection. There are other forms of projection, but basically 99% of the time, this is the one we're going to use. And the perspective projection, in it, you basically have 2 planes on the z-axis, that's where you're looking at, that define what you can see. The z-near is basically close to the lens, and before this plane, you can't see anything. And the z-far is very, very, very far away, after which we just assume everything is infinitely small and cannot be seen. So everything that you can see in the camera is between z-near and z-far. And then the camera also has the field of view, which is this angle of how much you can see. And if you put these 2 together, you can imagine this shape, which is kind of like a trapezoid. That's called a frustum. That's basically the space that can be seen in the camera. But, as I said, we really don't need to care too much about these details this time because we're going to delegate all this to the GPU. It's going to do all for us. We just need to understand if we see a matrix, that's what it means. But it's going to be done for us by the GPU. Good guy, GPU. Now let's go a little bit more specific into Flame 3D code because I feel it's still a little bit too abstract. And in Flame, we're going to get to the concept of a mesh. And that's basically the most basic thing we're going to render on the screen. But before we get to mesh, we start with a vertex. So a vertex is a point in space. Very, very basic in 3D space, right? A 3D point. And that's the key ingredient that's going to make the meshes that we're going to render. Now, this is a version of the actual vertex class from Flame 3D. And you can see it has a lot of things. It not only has the position, because what this class is basically a byte buffer. It's the storage of all elements that we're going to send to the GPU to tell it what to render. So this is kind of data structure that we're propagating to the GPU. And as you can see, it has the vector 3 position. That's where it is. But then not only that, it has a texture coordinates and color. So these two things are going to tell the GPU basically what color to render that triangle, either based on a texture or based on a flat color. Now, one thing to demystify here is that these vertices are not like pixels. We're not going to say the color of each pixel like you might do in 2D. These vertices are just the edges, the vertexes, the border of a triangle. So what the GPU is going to do is going to linearly interpolate your colors to paint that triangle. So if all your 3 vertices of the triangle are the same color, you're going to get a flat triangle of that color. That's probably what you're going to do, or you're going to use a texture. If you want to put different colors on the vertices, you get some pretty like stuff like the ones Renan does with the shaders. But probably you either have a flat color or you have a texture. And you can see the texture is not specified here because it's specified at the surface level, which you're going to get there. But what you do specify here is the coordinates of the texture. And that's basically, so a texture is just a 2D picture that we're going to stamp on 3D surfaces. And the way we stamp it is by using this 2D coordinates of the picture mapping to this vertex. So basically, if we had a triangle, and we could say one edge of the triangle maps to here, one maps to here, one maps to here, the picture on the triangle would be this triangle here. If you do something different, it's going to distort this image to conform to the shape that you want to draw. Next, we have the normal. So another vector tree. This is the normal to the surface of the vertex you're drawing. So if you have a surface and you have this vertex, right, on the edge, it's going to be an edge. So the normal would be the perpendicular vector coming out of it. Now, why the hell do you need to specify this, right? It doesn't matter to render a triangle where the normal of the triangle is. We specify this for lighting. So I'm going to show that another very important thing in 3D is that we have basically a lighting engine that we want to specify how things should be lit and how they should react to light. In order to do that, all the physics formulas that define this require us to know the normal. So that's why this information is encoded there. And then finally, we have 2 vector 4s that are intimately related that are called joints and weights. These 2 are to do skin animations. So it has to do with animations that have a skeleton. And I'll explain that later, but it doesn't matter. If you're drawing static things, it doesn't matter. And then all these guys, all their bytes, are packed together into this storage, which is about 16 bytes, or 12, I think, with all these things. But we don't send each vertex to the GPU. That will be too many trips, right? We want to pack them together. Oh, yeah, let's actually talk about this first. We're going to pack them together into a surface. The surface, before I said it was triangles, but it basically can be a triangle strip because you can have multiple triangles from a single surface. So for example, if you're rendering a cube, each face of the cube is a square, right? Or a rectangle if it's a different size cube. But we can't draw a rectangle, so what we do is we draw 2 triangles instead, right? And you can have any number of triangles. So instead of sending all the vertices 3 by 3, we send the whole array of vertices that represents the entire surface at once as a single byte buffer. So that's the list of vertices. There's some other stuff here, for example, indices. That's just so we don't repeat the vertex. So if you have repeated vertex, you can use indices to kind of identify them like a variable. And then we have the material. This is where the texture is. So if we're using an image, the byte of the image will go in here and will apply to the whole surface. We, of course, don't want to replicate that for each vertex because the whole surface uses a single texture. And then we have this joint map, which again has to do with the skeletal animations that we don't care about right now. And that's creating the surface. And then we send all that to the shaders. So the shaders is the language within OpenGL that allows you to do operations on the GPU. The same way that you have your Dart code doing stuff on the CPU, and you can write, equations and stuff, and that's going to run on the CPU. The shaders is the way you run code on the GPU, basically. And what they're doing here is multiplying all those matrices for you. Now, when you render something with Flame 3D, it already has these two shaders for you. So theoretically, you don't need to write any shaders to do your game. If you want to write a shader, you can get some custom behavior, but it's really not necessary. So that's why I'm being very, I'm just showing that this exists, but I'm not going to explain how shaders work. If you want to do something custom, you're going to have to look elsewhere. So I have a resource here. It explains very well how shaders work and how you can build your own. Just as an example, this is one of the shaders, and it is the most simple one possible. It doesn't have the joints for the animations, and the other one is even more complicated. So I don't want to get into that. But basically, what you need to know is that all these bytes that we're sending to the GPU are input to this procedure, this code language, that is transforming that into the pixels you see the screen. So this is what's doing all those transformations. This is the yellow line that we didn't know about. Okay, so we have the surface, but I promised you mesh. I said the most basic thing that we render is a mesh. So a mesh is basically just a 3D object, right? So what it has is a list of surfaces. So for example, if you have a cube, it has all the 6 sides. Basically, that's it. It also has an AABB. That's a very common term within 3D programming, and it stands for axis-aligned bounding box. So it's basically the rectangular box, the smallest rectangular box that your shape completely fits inside. And this is just used for either collision detection, but in our case, for culling, for a simple pass to determine things that are like behind the camera or outside the camera that we can't see. We just want to quickly skip those things. So we don't want to do checks with the complex geometry. We just want this box as like a first pass. So we're sending this list of meshes to the GPU to render. So what does that look like? I said a lot of complicated things, right? But it's actually pretty simple to render. If you just want to render a cube, that's all you need. Because so in order to render the cube, you need to define all those triangles, right? So if you look at this photo from before, you can see that each face has 2 triangles. So basically, we're talking about defining 12 triangles, each one with 3 vertexes. So if you wanted to render a cube from scratch, you need to define that. Now, of course, I already did that on Flame. So we have the cuboid mesh, and this has all the list of vertexes. You can see it's huge, but it's pretty simple, right? Like it's just, you can very easily geometrically figure out all these positions because it's a square. So in your user code on game land, you just create a cuboid mesh, you tell us the size, and it will create all the vertexes for you. It's gone. And then you create a mesh component that's just the flame, tying into the flame component system, basically saying, render this mesh. So you can see all that boils down to very simple code if you want to render a cube shape specifically. Now, of course, you're going to want to render other shapes, right? And then basically you're going to have to define all those vertexes yourself, which, as you saw, it's quite a pain just for a cube, right? So you're probably not going to do that. So at this point, I would have 2 questions. First one is like, how define this vertex in a better way, because I don't want to do that manually. And the second question is, what about this lighting? I guess you can't see. But you can remember that the cube had some lighting on it, right? So we're also going to talk about that. Is there any questions in the meanwhile? What do you mean by observability? Yeah. So for me, one of the core concepts of Flame is that it's code first. I feel like a lot of game engines are like editor first, right, where you just drag and drop things. So I want things to be code first, meaning there has to be a code way to do things. So you have to be able to add a cube like this. Now, that doesn't mean you cannot have an editor, right? It's definitely not on my roadmap because, as I'm going to show, this is very bare bones, meaning there's a lot else to do first. But eventually, I could see there being like a 3D viewer or a 3D editor. What I do, honestly, I just throw things and then I run the game, and Flutter has graced us, the gods of Flutter graced us with hot reload, right? So it's actually way easier than in other engines to where you can just the Shift R and you get your new stuff. So I use the game itself to view where the objects are. But I definitely think an editor could be a potential thing. I know other people have been working on sort of editors for Flame 2D. So I wonder once we have this, if that can be expanded for 3D as well. Again, we're talking about very future deadlines here. More questions? Yeah. Like the currency? Is that a file format? I see. Yes, I have. So I'm going to talk about loading models on different formats in a bit. I assessed all the available. I kind of remember that one. I kind of went for the open source route, so I picked OBJ files and GLTF files, which I believe are quite similar. I didn't want to go into the other ones because there's just so many and they were not open source. But of course, like anyone can make a loader into this structure. So I would envision that eventually Flame would, have loaders for all different kinds of formats. But that's why we need the community to help. But we'll get there. I'm going to talk about models. So the two questions were, where does lighting come from, and the models. But let's talk about the lighting first, because that's the order I put in the slide. So in order to render anything, you need light, because without light, you can't see, right? We all know that. That's physics. So currently, we have two types of light. The first is ambient light. That basically applies a static light to everything. So that's kind of what you would expect if you didn't know you could do lights. If you don't add this one, everything will be black. I just need to say this. Otherwise, you might be questioning why things are not showing up. But you don't really need to have that one. If you want to do like a darker style game where everything is lit by point lights, you can. The point lights are the realistic lights where it emits light all directions from a point and then attenuates. In real life, everything is a point light. But it just so happens that we have, for example, the sun that's so far away and so bright that it kind of becomes an ambient light. So that's a simplification that we have. In most games, you're going to have some sort of ambient lights, and then you might have some different point lights if you want to have like a specific light source that's a little bit brighter. And as you would expect with a light source, you can specify the color and the intensity. For the point light, you can specify the position. The ambient, obviously, by its own nature, doesn't have a position. It's everywhere. Let's look at what it looks like into the component tree, because it gets a little bit complex. So we all know from Flame, which is in blue here, like the normal Flame, we have components. And then we have position components, which probably, most components you have in Flame 2D are position components. They come in with that vector 2 position, which is their 2D position. That's all for 2D worlds, right? So luckily, we have this base class component on Flame that doesn't have anything, and that's what we extend into component 3D, which is the equivalent of the position component, but for 3D. It has the 3D position and also the 3D orientation of the model. Similarly, in normal Flame, you have world. We're going to have world 3D. And you have the camera, you have a camera 3D. And these things just extend their 2D counterparts. So very simple so far. Now, where it gets complicated, I kind of created this distinction. I'm not sure I still like it, so we might change it. But I thought that it made sense that the lights are not the same thing as the objects, because the objects are rendered themselves, and the lights are actually not rendered at all. They just change how other things are rendered. So I kind of separated them. We might bring them back together. But what really matters is you have this abstract component 3D class that can really be used, and then you have to choose either, if it's an object, it has its like render things, and if it's a light component, it has a special treatment within the engine. So probably in other engines, the light wouldn't be a component in the same sense that the objects are a component, but within Flame, we're trying to adapt this to our like philosophy, and where everything is a component, so that's kind of how it's designed. So the lights can be ambient or point, which already explained the difference. There exist other types of lights. Again, actually, everything is point, but there are other simplifications of lights. So for example, if you want to have sunlight, that would be a possibility that we haven't implemented. And then the object 3D, where this is how the mesh component. That's how we render that cube. But we also have a model component, which I'm going to show in a bit. That's how you load the files, like potentially the USD file. Now, how the lighting actually works, again, I'm not going to explain this because it's based on a little bit complicated physics formula, so you might have to dust off your physics books if you want to remember this. But basically, it's all done by the shader. It's all done by the GPU. You don't need to worry about it, right? We just specify where the lights are, and we have these transformations on the shader that calculate how things should be lit based on where the lights are. It's kind of like the light is not active. It doesn't do anything. It's actually the objects being rendered that kind of look up where the lights are. So it's a different system. Some things we don't support is we cannot have an arbitrary number of lights because I'm still trying to figure out how to do dynamic arrays in the shader language. So right now I think I added 3. If you want to add more, it's extremely trivial, but you have to kind of copy and paste some code for now, which I hate doing, so I'm trying to get the arrays to work. We also don't support some more advanced parameters, and we definitely don't support shadows. So there's no occlusion yet. That's an even more advanced formula than this one. Another thing here is that PBR stands for physics-based lighting. That's like the underlying model behind what we used. And one interesting thing about this model is that every material not only has its color and texture like we saw, but it has a few parameters that define how light applies to this object. So for example, how metallic it is, how reflective it is, that kind of thing. So we're gonna see some different renderings using different types of PBR parameters. Another thing that affects lighting is the normals that I talked before. And there are 2 different ways of doing normal. The key problem here, let's say, is that the normals are per vertex, right? But if you think of a 3D shape, you always think of normals for a surface, right? You have a surface and you have a normal. How can you put a normal into a single point? Well, you can't. You have to tie that back to the surface. So there are 2 ways of doing that. The simplest to understand way is face normals. If you're using face normals, on each vertex of each face, you draw the normal relative to that face. That means that this corner here would actually be 3 vertexes, right, that are different. Because each vertex on each face has a different normal. So the front face would have a normal this way. The top face would have a normal that way. This face would have a normal this way. That means we cannot use that optimization of the indexes, right? Because even though this vertex is shared across multiple faces, multiple times, each time it has a different normal. So another way to do the normals is to do the vertex normal. In that way, we kind of do the average of the normals on that point. None of them are more or less physically correct. They could both be argued for. They just have different results. So this gets a more smooth, and this one gets a more like diffuse looking thing. Now this doesn't matter that much. I have here an example of a model that I loaded. You can see it looks totally different because of those PBR parameters. So this cube was defined as being very metallic, so it has a completely different appearance than these ones that I created using the cuboid mesh. So basically defining the vertexes by hand. Again, just something that you should have in the back of your mind. If you're having different lighting than you expect, it might be because you have the different normals pointing differently. I actually forgot what this video is, but let's watch. Oh yeah, this is a demo of the lighting. that I perfectly cropped with no errors. Oh yeah, actually I failed to see the moving. Oh, thank you. But the light is actually, the green light is moving. Yeah, I don't know if you got to see that. Maybe it's impossible. Yeah, there's a green light. So there's a static light, and then there's a green light moving here. I should have made that more intense. I didn't realize. There's also like a reddish light. You can kind of see they're all blending. So this is how you do lighting. This is what lighting looks like. Thank you. Now let's talk about models, because we don't want to define those coordinates of all the vertices by hand for every single element, right? So we want to grab some from the internet, like the teapot that we did last time, and we want to just render it. So how do we do that? Well, we have to parse some file formats. And basically, as I explained, I picked two of them, the object and the GLTF, also called GLB. I'll explain the difference. These two is what we have right now. But there are others, like FBX. I guess I forgot to pick another one to put here. There's one called Colada, and there's USD. So eventually we could have all of them, but right now we have these two. I'll talk about the object first, because it's literally the simplest possible file you can imagine to describe a 3D object. It's literally just a text file where you have each line is the coordinates of one vertex, right? These are comments that are just ignored. Then you have V, that's the vertex. Vn is the normal. Vt is the texture coordinates. And then the material. And then you define the surfaces, which are the triangles. This is in the format V, Vt. So this is kind of defining, like predefining the coordinates and assigning, let's call an ID, that's an index to it. So this one will be index 0. The next one will be index 1. And then this is basically saying, make me a triangle, use the vertex ID 1, ID 2, and ID 3, use the texels ID 1, 1, 1, use the normals ID 1, 1, 1. So this is basically the simplest possible format that you can think of to describe these vertexes and their coordinates. So I first implemented this one. Now, I actually did this a while ago when I started working on this, and I had already shared I think it was on a FlameCon, this video where this is the first 3D proper game that we make. It is very, very simple, but I wanted to make a game like beginning to end with like menus and sound, kind of have it all working. So this is called Defend the Donuts. It's a very stupid idea. It's basically you have this space donuts that you have to protect, and you protect it from some ships that are going to show up and start attacking it. I did this because I found these models as object files, and because it needed no animation. Everything here is done by hand, so the rotating donut is not an animation. I'm just rotating it myself using the matrices for rotation. And then eventually, should have made it quicker, I guess. I promise a ship will show up. Yeah. Well, it's give you a briefing room, right? To get used to it. Yeah, there you go. Ships are approaching, and then you can shoot. With very simple collision detection just for the bullets, so you can pass through things because we don't have physics. But I wanted more. And if you look up models online, you're probably not gonna see object files because they're too simple and they don't support a lot of things like animations and skeletons that I was talking about. So there are other formats. So the one I picked was GLTF. It is defined by the same open source committee that defined OpenGL, but it's not specific to OpenGL. It's a completely independent thing. But it stands for GL, graphics language, transfer file, or transfer format. There are two versions of it. The GLTF is a text file version, which is a JSON that describes the things. But it's kind of half and half, because the JSON part just describes the basic properties, but the actual vertex data is in a binary format inside the JSON. And then the GLB is a complete binary version of the same structure. So it uses this concept of byte buffers within the file, because it would be too big if you were to, within the JSON, have like a JSON array with all the vertexes. That would be extremely big for the types of models that we're talking here. So it defines the metadata as a JSON, but the actual vertex data, it just puts the bytes there. So it's a little bit harder to parse, as you might imagine, because I just have to look up those bytes and figure out what they mean and convert that into the Flame structure. But it supports a lot more things. It supports scenes and nodes, it supports animation. So in order to kind of support that, I created a new component called model component that uses this model data structure. This is a little bit more involved than a single mesh. So the idea of a model is a mesh would be, as we saw, like a 3D solid, right, like a cube. And a model would be a combination of multiple meshes that form what would be in Flame 2D a component. So one character or one gun or like one thing that exists by itself in your game. So all these meshes like move together, basically. It also supports animations. So it has a list of animations that come from the file, and then from the model component, you can do play and play any of these animations, similar to Rive components, if you use Rive with Flame. It has a list of nodes. So instead of being a plain list of mesh, it actually has a tree structure, because some nodes depend on the position of the previous parents nodes. So it's just a hierarchical organization structure for the meshes. But basically, every mode, it might be just a grouping, or it might have a mesh. So you can think of a node as maybe a mesh, but it's organized in this tree structure. So it has the transform. That's, again, how it's rotated, translated, and positioned. Remember, whenever you see matrix 4, you don't need to go inside, look at the numbers, but know that that means translation, rotation, and scale, right? It also has the joints data that's used for a specific type of animation, which is skeletal animation. And then it has the animation here, which is used for both types of animation. The animation is basically, again, a set of matrices that describe how the vertex move through time. And it's basically a loop. It's always a loop that you're going to be playing. So let's look at a video of some models being loaded with lighting. And one of them has some animation there. So this is a real animation here. It's not me doing the transform. This animation is part of the model file being played. We have a very metallic cube and some characters. And also you can move the lights. I don't think I mentioned that, but yeah, obviously you can move the lights. Yeah, that's what we got. Thank you. But there's a lot we don't have, especially polish. So again, this is very, very bare bones. For example, I couldn't figure out how to do arrays. I think it doesn't work with Flutter GPU right now. So I had to do this disgusting nonsense, because I'm very creative and I can do arrays without arrays. Yeah. There's SSBOs are like dynamic arrays. I cannot even do static arrays to begin with. We don't have shadows, we don't have physics. It's probably not optimized. Some stuff I just got it working. It runs really fine with that example, but as we scale, we might need to do some optimization. Anyway, this is a call for help. This is like, if you are interested in this kind of stuff and you want to be a pioneer and you want to not only build your game, but also probably send us a lot of PRs and fix some bugs and contribute, I invite you to join our cause and build some 3D stuff. I guess I'm out of time because Spider is standing right next to me. I'm going to skip all the learnings and just say questions. We don't have time for questions either, so I just skip to the end. Thank you very much.